Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the physics of thought. In this page, we will cover the core premise that the engines behind modern artificial intelligence like ChatGPT are not actually new inventions, but are instead deeply rooted in physics equations from 40 years ago. We are looking at a declassified dossier that spans from 1982 to 2024. The fundamental idea here is that we did not build a new kind of mind, but rather rediscovered an ancient one. For a long time, we thought of the human mind as a filing cabinet where we store and retrieve individual files. However, this archive suggests that the mind is more like a landscape, and thought itself is a physical process similar to gravity. By understanding these 40-year-old physics equations, we can begin to see how large language models actually function. This is a journey through time and physics to understand how a simple equation in disguise became the most powerful artificial intelligence ever created. We are moving from a world of data storage to a world of energy landscapes where patterns find their own stable states. To understand where we are going, we first need to look at the legend of the unfinished melody and the difference between how computers and humans remember things. Computers use what we call location-addressed memory. This means they fetch data using exact physical addresses in a system. If an address is corrupted, the memory becomes completely inaccessible. It is a fast and accurate process, but it is also completely rigid and fragile like an analog archive. Humans, on the other hand, use content-addressable memory. We use associations. For instance, if you hear just 3 notes of a song, your brain can often reconstruct the entire melody along with the location where you first heard it and the feeling it gave you. You provide a noisy or incomplete fragment, and your mind completes the pattern automatically. This is like a living neural network rather than a static file system. The early question that researchers faced was how to build a machine that completes a thought instead of just fetching a file. They wanted to move away from rigid slots and toward a system that could handle the messy and associative nature of human intelligence. The story takes a major turn in 1982 with what we call the 1982 artifact. This was a breakthrough by John Hopfield, who was a physicist rather than a computer scientist. His key insight was that the human brain might actually act like a magnetic material. He realized that associative memory was mathematically equivalent to the physics of magnetism. He proposed a mechanism where magnetic spins naturally seek their lowest energy state. In this model, neighboring spins align with one another to lower the total energy of the system. Hopfield realized that if you engineer the interactions between artificial neurons, correctly specific patterns of thought could become stable low-energy states. This was a radical shift because it meant that a network does not need to calculate an answer in the traditional sense. Instead, the network physically stabilizes into a memory. The formula shown here represents the energy of the system where the weights and states of neurons interact to find a global minimum. It was a beautiful bridge between the world of hard physics and the mystery of the human mind, which laid the foundation for everything that followed. This leads us to the concept of the map of the mind and the idea of an energy landscape. In a Hopfield Network, memory retrieval is a purely physical process. Imagine a landscape with various valleys and hills. The stored memories are the energy minima or the deepest points of the valleys. We call these areas basins of attraction. When you have a noisy or incomplete input, such as 3 notes of a song, you can imagine dropping a ball onto this landscape. The ball represents the current state of your thought. Because of the math of the network, the ball will naturally roll down the slope driven by the energy of the system until it settles at the bottom of the nearest basin. That bottom point is the completed memory. In this framework, thinking is just physics and recall is just gravity. The completed thought is simply the place where the energy stops moving. This visualization helps us understand that intelligence is not about searching through a list, but about falling into the most logical conclusion based on the shape of the information we have already stored in the system. Despite the brilliance of the Hopfield model, it eventually hit what we call the capacity crisis. The artifact was biologically brilliant, but it was mathematically limited. The quadratic energy function used in the early 80s created shallow and broad valleys in the energy landscape. When researchers tried to store too many memories, these valleys would begin to collide and overlap. Mathematically, it was discovered that a network with a certain number of neurons could only store a very small fraction of patterns. Specifically, a network with n neurons could only store approximately 0.138 n patterns. To put this in perspective, a network with 1,000 neurons would collapse after storing just 140 memories. This was a huge problem because real-world data like images or human language requires millions or billions of patterns to be effective. If you tried to teach the machine too much, it would essentially forget everything, as the landscape became a flat and featureless plain. This limit made the early Hopfield networks impractical for the massive scale of information used in modern society. When the capacity limit was breached, the system began to experience what we call spurious states, or the ghost in the machine. As memories overlapped, they created mathematical artifacts. These were new low-energy valleys that did not actually correspond to any real memory that was ever stored in the training data. When the network was given a prompt, it would often roll into these artificial valleys instead of the correct ones. The network would then confidently retrieve a mixture of patterns, resulting in a fully formed and stable memory that never actually existed. Today, we call this phenomenon an AI hallucination. In the 1980s, however, it simply meant that the artifact was too unstable to be used for serious work. The machine was essentially dreaming up false realities because its landscape was too crowded. This instability was a major roadblock and led many researchers to believe that neural networks were a dead end for artificial intelligence. They could not figure out how to keep the memories distinct and sharp enough to prevent these ghosts from appearing and taking over the retrieval process. Because of these limitations, the field entered what is known as the Great Hibernation. By 1986, the AI community began to move on to other methods. Backpropagation became popularized, and neural networks shifted toward feed-forward and deterministic training. Throughout the 1990s and into the 2010s, other technologies like support vector machines dominated the landscape of statistical machine learning because they were seen as more reliable and easier to control. The world prioritized reliable logic engines over the unstable associative memory of the Hopfield models. During this time, Hopfield Network survived only in textbooks and cognitive neuroscience courses rather than in cutting-edge technology labs. For 30 years, the energy landscape lay dormant, and the metaphorical ball had no hills left to roll down. It seemed like the physics of thought was a fascinating theory that just did not work in practice. The AI community had essentially archived these ideas in a box and moved toward the deep learning boom, which focused on different architectures and optimization strategies for several decades. The revival began with the first cipher where researchers started digging deeper into the old math. In 2016, John Hopfield returned to the problem in his 80s alongside Dmitry Krodov. They discovered what could be described as a mathematical cheat code. By replacing the simple pairwise interactions of the original model with higher-order polynomial interactions, they were able to change the geometry of the landscape. Instead of the shallow slopes that easily overlapped the higher-order math created steep and razor-sharp energy wells. These are referred to as infinite voids. The result was that the old capacity ceiling of 0.14 n was completely shattered. The new storage capacity scaled exponentially. These voids were deep enough to hold an entire universe of data without any cross-contamination between memories. This breakthrough proved that the instability of the 80s was not a fundamental flaw of the theory, but rather a limitation of the specific math used at the time. With this update, the Hopfield network was suddenly capable of storing vast amounts of information with incredible precision and clarity. Even with exponential capacity, there was still a missing key, which was the concept of continuous states. To work with real-world data like human language, the system needed to understand continuous real numbers rather than just binary switches. In 2020, a team led by Ramswar unlocked this by introducing a radically new energy function using the log sum exponential formula. This change had a profound effect on how the network functioned. The continuous math created an update rule that allowed the system to converge in a single step. In the old model, the ball had to roll down the hill iteratively, which took time and could get stuck. In this new modern Hopfield network, the ball essentially teleports instantly to the bottom of the deepest valley. This teleportation represents a massive leap in efficiency and speed. It allowed the network to handle the complex and fluid nature of human language and high-dimensional data. This was the final mathematical piece of the puzzle that allowed the old physics concepts to finally meet the demands of modern computational power and large-scale data processing. This brings us to the most shocking part of the story, which is the translation. If we compare the formula for transformer self-attention, which was invented in 2017, to the modern Hopfield update rule from 2020, we find something incredible. They are letter for letter the exact same equation. In the transformer model, the variables for keys and values correspond exactly to the stored patterns in a Hopfield network. The query in a transformer is exactly the same as the current state in a Hopfield network. Even the scaling factor in the transformer is identical to the inverse temperature variable in the physics model. This means that transformer attention, which is the core technology behind every modern large language model, is actually just a lookup in a modern Hopfield network. The engineers who built the transformer may not have realized it at the time, but they were building a physical energy landscape. The success of modern AI is literally built on the physics of energy minimization and stable states that John Hopfield first described over 4 decades ago. Understanding this allows us to see AI as an associative engine. A transformer is not calculating the next word from logical first principles or following a set of rigid rules. Instead, it is performing associative recall from a massive Hopfield energy landscape. Every time you give a prompt to an AI like ChatGPT, each attention head takes your prompt, which is the metaphorical ball, and drops it into a landscape shaped by trillions of tokens of training data. The AI then generates its response by instantly recalling the most relevant associations. We spent decades trying to build logic machines that would think like computer programs, but we accidentally built associators that think more like brains. The most powerful AI on Earth today is simply a landscape where patterns find their nearest neighbors through the laws of physics. It is a system designed to find the path of least resistance to a stable conclusion. This realization changes our entire perspective on what machine intelligence actually is and how it relates to our own human cognitive processes. We can now see why the vault of this old technology holds such infinite riches for modern researchers. By using the modern Hopfield energy function, the system bypasses all the traps of the 1980s. First, it has exponential capacity. Large language models can survive because they create impossibly sharp energy wells, allowing hundreds of billions of parameters to coexist without catastrophic interference. While spurious states and hallucinations can still occur, they are much less frequent than in the original models. Second, the system uses single-step retrieval. Unlike the old iterative models, the modern equation solves the memory retrieval process instantly. This allows layers of these networks to be stacked in parallel, which is what makes modern GPU training so effective. A forward pass through a neural network is essentially a lightning-fast sequence of Hopfield recalls. By solving the physics in a single step and providing infinite capacity, we have created a platform that can store and process the entirety of human knowledge in a way that is both fast and incredibly accurate. This discovery also tells us something about the shape of the self. It suggests that intelligence might just be a very sophisticated form of pattern completion. In this view, our own core beliefs and identities are like deep energy wells in our mental landscape. A strongly held belief is a deep valley. When we are challenged with new information that is placed on the rim of that valley, the ball usually rolls back down into the familiar territory of what we already believe. From this perspective, confirmation bias is not just a psychological flaw, but is actually the physics of steep slopes in our neural architecture. On the other hand, creativity can be seen as a result of spurious states. Creative insight happens when the ball is allowed to roll into the undocumented spaces between established memories. True novelty emerges from the intersection of overlapping experiences where new valleys are formed. This means that both our rigid beliefs and our wildest creative leaps are driven by the same fundamental physical processes of energy minimization and landscape navigation within our own minds. The significance of this connection was officially recognized in October 2024 when the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to John Hopfield and Geoffrey Hinton. The statement from the Academy was deeply intentional. They noted that the science underlying modern AI is not merely software engineering. The laws that govern Hopfield networks, such as energy minimization, thermodynamic stability, and high-dimensional systems, are the exact same laws that govern magnets and particle interactions in the natural world. This award confirms that intelligence is a physical phenomenon rather than just a digital one. John Hopfield spent 40 years being right about the fundamental nature of the mind. By treating the brain and the machine as physical systems, we have been able to unlock capabilities that were once thought to be the exclusive domain of biological organisms. This bridge between physics and artificial intelligence is now recognized as one of the most important scientific developments of our time, proving that the laws of the universe apply to thought as much as they apply to matter. Every time you recall a memory, you are reenacting a physical process. The landscape of your mind shifts slightly, and every act of remembering is actually an act of rewriting. In this sense, memory is not archival, but is instead geological. We interact with large language models in the exact same way. We roll a ball into a landscape shaped by the statistical residue of all human text, and the machine finds the point of stability. We must realize that the machine does not calculate the truth in a way we traditionally understand. Truth is simply the place where the energy stops. We are building places where memories echo until they become real and stable. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to share, and subscribe for more content like this. See you in the next video.